Okay, this is a continuation of the previous video in which we introduced a whole nother layer of mappings onto our Bessie structures, onto our two cycles, our mirrored structures, and our AMP structures. Great. And we spent a fair amount of time talking about the supercut. Over here, the C/S stands for Charlier shuffle, which we've used extensively throughout this semester, and the S stands for supercut. So we talked about the supercut, as I mentioned, extensively, so that one's kind of behind us. But the supercut is an automorphism on two cycles, and that's what we saw. I want to point out the FL. You'll see that above our three primary structures. FL stands for entire packet flip. And we've made reference to this in the past, that if you have a packet of cards and you flip it over like that, it just reverses the order of all of the cards. So this becomes the new top card all the way down to the bottom card, which was originally the top card. Okay, so that's what packet flips do, of course. Now, we've seen that two cycles, mirrored structures, and AMPs are invariant under packet flips. Or in other words, under sequence reversal, these structures remain of the same kind that they began as, okay? So if you reverse a two cycle, you get a two cycle. If you reverse a mirrored structure, you get a mirrored structure. If you reverse an AMP, you get an AMP. So the packet flip then would constitute an automorphism on each of these primary structures. Okay, great. So now let's talk about some of these other mappings and what you might use them for. These are all very powerful because they involve flipping cards. And the moment that you flip cards, that introduces additional complexity to the packet structure itself, and also to the perception of complexity in the mind of the observer. Okay, so I have here a two cycle. Okay, so you can see it's a two cycle relative to card values being the same. Okay, so that would put us over here. We're starting over here. And if you notice, we have what's a PFRS. And these acronyms are meant to just kind of remind us sufficiently of what each of these mean. You'll notice down here that because of my expert three-hole punching, I actually cut off the bottom of the P here. So that's a PFRS. And what that stands for is if you have well, here we're going to start with a two cycle. If you push over half the cards, and then the right side or the left side can be flipped. And it's completely arbitrary. You could leave that up to the spectator to decide, which gives them another degree of freedom in this whole thing. I apologize that I have blue pen all over my fingers. I've been playing with, as you can tell, permanent markers, and they call them permanent markers for a reason. Okay, so here we are. I pushed off 50% of the cards, and so we can flip, let's say, the right-hand side. And now I can actually do a random stack. So I can stack it in this order. So that actually completes a PFRS. Okay, now the claim on the diagram, of course, is that we have now landed in the world of mirrored structures. Okay, so here we have, of course, the ace through six. And so what if this is mirrored, this needs to be the black ace over here, which it is, of course. In fact, we can just have you peek on the back side and you can see that indeed this is a mirrored structure. Okay. Very good. Now, of course, if we reverse that, we can get back over to a two cycle. Now, it may not necessarily be the exact same two cycle. It depends on those choices as to exactly what the packet looks like. Okay, and you can kind of play with that and realize, oh, yeah, you may not actually reverse what we just did. Why don't we follow this one-way street over here back to 2 cycles, okay? So an LRF. Okay, so what this is, it's just an LR shuffle. Okay, left, right, left, right, left, right. And now it's listed down here. We can flip the right pile or the left pile and then randomly stack them. So why don't we flip the right and then what we want left on right. Okay, very good. We'll stack them in that order. Okay, now that's guaranteed to take us back to a 2-cycle. Okay, and we can see that it's looking pretty promising already because we need P-equivalent cards to be C-equivalent. And C-equivalent here means that they have the same value, right? So you can see that this is looking pretty good because these are the 3 last cards in the first cycle of 6 cards, right? And they have to be of the same value as the ones over here. And so that would mean that these 3 here have to be of the same value as those over there. And you can check that they are. So they're just kind of mirror images there. Okay, so that's a mirrored structure. Now, I do want to point out right at this moment that we began with a very transparent packet structure on purpose. You can begin with that packet structure and quite honestly, still finish with incredibly surprising outcomes. But if you were to begin with a random packet, which we have before, all of this would look far less transparent than it does right now. So these cards would be kind of random, and so would those actually. And so if we had a random packet of 12 cards, and we had just kind of jotted down on a piece of paper, kind of facing us, the identities of the cards, maybe take them in pairs and treat it as an AMP. We could go through and mix it to, wazoo, and use any or all of these mappings here and finish with a perfect matching up of those original ones that we noted. Spectator doesn't know that you're imposing a AMP structure on it. So in that case, when you bring out your piece of paper for the reveal, it's just astounding that you could possibly have guessed what the final pairs of cards would be after just tremendous mixing. But for now, for educational purposes, we're looking at a very transparent packet, and that's just fine, even though it's actually going to get fairly mixed by the end, as you'll see. Okay, so that takes us back to a 2-cycle, and then remember, at any point we could choose to or have the spectator say flip. And so you could just flip it over, and now from this point on, work with the packet from the other side. Okay, so what should we do here? I guess we could do a supercut, if you remember what that is. So that's where you just count off any number of cards, you flip those, and then you just go right into a Charlier shuffle, right? And if you remember, that actually preserves 2 cycles, which is most remarkable, actually. So why don't we kind of check it here? So like, well, here we see a 6 here. So we need to see, so excuse me, so okay, 2, 4, 6. So we need to see a 6 right here. Whoop, I'm sorry, I grabbed the wrong one. We need to see a 6 right here. I don't know how to count, right? Okay, because we have 2 above the 6, which would give us a cycle of 6. I apologize for that 6 being everywhere there. So this actually is a 2-cycle. So our supercut did preserve that as desired. We have talked about, let me just remind you of our original primary structure. And if you recall, the LR shuffle will take an AMP to a 2-cycle. And the way that we reversed that in the past was we would perform a Faro shuffle. Okay, that's where you break the cards in half and then you perfectly interlace them. Well, that particular shuffle, it takes a bit of practice to do it successfully. And so that might be kind of a rough way to go if you're going to reverse the actions of the LR shuffle. So even though I demonstrated it several times, it may have been a little unfair of me to throw that on you because it does require some practice to acquire that skill. So what we're doing over here is a true, well, it's also in some sense, it's like the true reversal of the LR. So, what I'm recommending then is you can master the Faro shuffle if you like. It's very fancy and it adds some flair to what you do. Or you can go with this much safer route and not really ever make any mistakes. So we're looking at let's see, we're looking at 2-cycle. So we're trying to get over here to a DMP. Okay. So I don't know how well you can see that, but what I've done is I've drawn a 2-cycle structure, just a quintessential one. It only has 4 elements. So it's 1, 2, 3, 4, 1, 2, 3, 4. And then I just show you what the dealing would look like. Okay, so I may just slide this over a little bit. And so we're going to go 1, 2, 3, 4. 1, 2, 3, 4. Oh, I'm sorry. Come on. We need to go. We need to go 6. Okay, this is a good learning experience for all of us. Don't follow my quintessential example there. We have a packet that has cycle length 6, not 4. Sorry about that. So I'm going to actually have to move that quite a bit here. So we're going to go 1, 2, 3, 4, 5, 6. Very good. And then 1, 2, 3, 4, 5, 6. Now, if I've done it correctly and haven't made mistakes earlier on, these should all be p-equivalent, actually. So the 3, this better be a 5. Happily it is. These need to be the same value, which they are, and so forth. Okay, so what that means is we truly have arrived at a DMP. And so recall, a DMP is where you have distinct mirrored pairs. So just as we do here, we have these mirrored pairs. And now when they're stacked together, it's called an AMP, right? So it's called an AMP when we stack them. And I have this note here of a random stack. And that truly is the case. So if you just pick these up in whatever order you like, you can pick them up in whatever order you like. It doesn't actually matter. Try not to drop them like I seem to do. You're guaranteed to get an AMP, okay? And so that's where we are then. We're at an AMP. I do want to add that we just did a random stack there, but we could have done the following as well, which kind of ramps up the impressive nature of the mixing. We could have randomly flipped and stacked those. So as I was picking those pairs up, I could have just asked the spectator, do you want this one in its current orientation, or do you want me to flip it before I set it on the packet? So you could go around and pick those up, the pairs of 2, in any order that you wanted and with any orientation. So you could have flipped any one of them and then stacked them in a random order, and it would still be an AMP, okay? So anyway, so we've actually covered 2 of those there, which is great. Now to get from an AMP back to a DMP, sorry about all these acronyms here. I have the push-off pairs. It looks kind of funny here, pop, but push-off pairs. So push-off pairs it means what it sounds like. So you just push off pairs. Now what's really nice is we don't even care where we put these. It doesn't matter, right? This is a DMP technically now, and so we can put them wherever we want. And at this point, if we would like to, we could actually do the very thing that I said. We could, like flip this and then set it over here. We could even flip them as we go. Oh, that's cool. I hadn't even thought of that. We could flip this as we go and then go like this if we want. Believe it or not, that doesn't destroy the AMP structure. And like I said, it's all the more amazing if we had random cards in our hands. It would be virtually impossible to imagine that those cards are in some kind of orderly arrangement relative to structure, that you have some idea as to what's going on. Okay, very good. So we've actually covered, oh, that's great. We're moving along here. Okay, so we've done all of those. Technically, we're over here now, right? Now we know how to get back to different places. So, for example, to go back to a mirrored, you'll remember if we have an AMP, which we do, we can go back to a mirrored by way of a mange. And what's nice is it can be either an over under or under over. Doesn't change anything. And at any point we could say flip and now work with the packet from now on with that orientation. So that takes us back. We're back in a mirrored now, okay? And so I wanted to show you. We've illustrated this one, and that's where I counted out the cards wrong. So we'll have to make sure we count out 6, not 4, for my example. Now I mentioned here that this is the LR and then kind of raised to a negative R. Okay. Now that is pure notation there. Okay. It doesn't mean actually like raising to a negative R exponent or something like that. Nor does it mean apply the inverse of the LR, shuffle R times. That was probably what some people might think. No, it's there just to remind us that we're going to deal out the cards the second time around in reverse order. Okay. So to undo a 2 cycle, what we do is we go 1, 2, 3, 4, 5, 6, however many we have, and then 1, 2, 3, 4, 5, 6, and then we get a DMP. Well, a mirrored is essentially a 50% coat away from a 2 cycle. So to bring a mirrored back to a DMP, we have to do like 1, 2, 3, 4, 5, 6, so forth. And then right there at the end, the last one, we have to count 1, 2, 3, 4, 5 going back. Okay. Now I may have confused you here, but you have to realize that I've drawn it as a mirrored structure to begin with. This is cyclic, and this is mirrored because I have 1, 2, 3, 4, 4, 3, 2, 1. Okay, so that's mirrored. So that's what it will look like. If I put these out left to right, it'll be 1, 2, 3, 4, and then I would set the next one here and then go that way, okay? And that will undo a mirrored structure, okay? So I'll move this over. And so we're gonna do 1, 2, 3, 4, 5, 6, and then 6, 5, 4, 3, 2, 1. Sorry, I'm not sure why I'm putting them above. What am I? It doesn't actually matter, but okay. Well, there we go. I meant to put them on top there. Now these should be equivalent again. So that should be a 3. These should be the same, which they are, and way over here, those should be the same, which they are. Okay, so with the diagram, I'm hoping that if people, let me move that over. You can't even see what I'm pointing at. Just reference how I've written out an explicit mirrored structure, and then the arrows will tell you which way to go at each dealing out. And at each dealing out, you're putting out half the cards. You're putting out a whole cycle length, right? Because a 2 cycle consists of 2 cycles, right? Okay, and so here we have a DMP. So once again, we could pick these up in any order. We can flip them. Now this could be dictated by the spectator, if you would like. And it really leads to quite a mess, which is good. We want a mess because in the end, um, when we use these shuffles, these mappings, these automorphisms and isomorphisms to work with this packet, uh, we really do need the observer to believe that the cards are sufficiently mixed or randomized. Um, and they have every reason to believe that if you think back to some of those mixing sequences that we've done. I mean, the supercut is got to be by far the most convincing way to mix a two cycle that's out there. And it's one that you even fool yourself as you're doing it, because as you do it, you think, there's no way that I preserved structure here. I'm sure I destroyed it. And then you look at it and it's fine if you've done it correctly. So, okay. So now what we'd like to do is I'd like to talk about what's called the two overcoats. Okay. And it ends up being an automorphism on mirrored structures. Two overcoats. Now these overcoats have to be identical. So if you coat 7 cards, let's say, you have to do it twice. You have to do coat 7 cards twice. Okay. And the whole idea of coating is based on the work of Colum McCaughey. I believe he's Irish or Scottish, so I may have slaughtered his name, so I apologize for that. But he's the one that came up with the idea of coating cards. And he developed a number of really interesting routines and discovered a number of properties and theorems involving coding. And so what I've done here is I've just built on to his work, okay? Because as far as I know, this is not known out there. You won't find anywhere where it says 2 identical overcoats preserve mirrored structures. Okay, so this is something I found on my own, and so I was inspired by his work. And now one thing that's nice about it is 4 overcoats. So he proved that given any packet size, if you coat 50% or more of the cards, it will return the packet to its original order, which is quite amazing, actually, because you're not only preserving structure, you're preserving everything. The entire packet is returned to its original order, okay? But to count out and transfer a number of cards 4 times can be a little laborious. It can get kind of boring or tedious for the observer and maybe even for you. So fortunately, this is just 2 overcoats. Will do the job. But you do have to have a mirrored structure to begin with, which we do. So let's go ahead and what we need to do is we need to choose a number between 6 and 12. So it needs to be more than 50% or more of the cards need to be coded twice. Okay, and so we could ask the spectator, okay, choose a number between, let's say, 6 and 12, to keep it interesting. And they say 7. Okay, so what you would do then is you just count out 7. 1, 2, 3, 4, 5, 6, 7. Put the rest on top, and then do it one more time. 1, 2, 3, 4, 5, 6, 7. Put the rest on top. And if it was mirrored to begin with, it will be mirrored still. Okay, and it's once again it's looking promising there, right? But this should be a red ace, which it is, right? So it needs to be the partner of that one for it to be mirrored, okay? And it's the same thing. If we flip it over, you'll see that it's mirrored, okay? So 2 identical overcoats will always preserve mirrored structures. So in other words, 2 identical overcoats constitute an automorphism on mirrored structures, okay? So boy, we have a lot of structure preserving and structure converting mappings that we've looked at so far. I just want to mention, and also I was going to show you the proof of that, okay? Since it is an original result, though I do stand on the shoulders of others there, but I'll show you the proof of that one. Now, I do have a couple of observations here. Oh, the first one is incredibly powerful. Okay, we have a mirrored structure, and I want an AMP, okay? So what I'm going to do is I'm just going to try to carefully do a Klondike. And of course, if you recall, right, if I have a mirrored to get to an AMP, I can perform a Klondike, and I get there. Okay, so I want people to understand this because this is really, really powerful here. So once you have an AMP, you can deal out even-sized piles of cards, or you can deal out just an even number of cards, and then use that as a separate packet with which you're going to work or move into a larger, a routine or performance. So, for example, let's see, we have 12 altogether. So what I could do actually is just do 1, 2, 3, 4, 5, 6. And so what that means now is I have 2 packets of 6 cards each that are AMPs, right? So I can go through, and since I know this is an AMP, right, I could change it to a 2-cycle. And once it's a 2-cycle, of course you can do a Charlier shuffle. Kind of hard to do a Charlier shuffle when you have 6 cards. It's not super interesting. I could coat half of them, right? I could do an LR shuffle, right, and do another one, and you have to realize that the spectator can say which one goes where. Maybe that one goes there, and then not to not belabor this, we could then deal out pairs, and you can point out, they go, boy, wasn't that lucky? I mean, that was pretty sweet that we actually dealt out the same value of those 2 cards. What do you think the chances are that we did it with the others as well? Well, the structure, so the probability is 1. They don't know that. So these will actually be of the same value, guaranteed. And these will be of the same value, guaranteed. Okay? So once you have an AMP, in fact, now it's an AMP again, so we can put it over here for use later if we wanted to. And also we could put it back on top of the original pile. It's still an AMP. But the point is, you could treat these two, you could use both of these following very different paths of mixing with automorphisms, isomorphisms, and then reveal something surprising in a different way, if you would like, okay? So for example, what we could do, so this one's already been used. This is mirrored. Excuse me, this is an AMP. So to get it mirrored, I could do a mange. And then once it's mirrored, of course, I can do as many LR shuffles as I like, and the spectator can decide that. And then I could do another mange. Where does that take us? Remind you. So if you're at a mirrored here and you do a mange, what does it do? It takes you back to a 2-cycle, okay? And then as a 2-cycle, we love the Charlier shuffle. Sure is kind of a mixed, messy little thing. And we could even do a supercut. Why don't we do that? So 1, 2, 3, go like this. And then we could say, oh, give another number. 1, 2, 1, 2. And then, since this is a 2-cycle, what I can do is I can just put out cards like this, right? And you maybe can anticipate what's going to happen. Assuming I haven't made a mistake, these should be C-equivalent cards. So that should be a 2. This should be a 6. And then this one, of course, is a 4. So that's a completely different way of revealing your successful pairing of identical values for those cards. Okay, and so that all came from an AMP being just subdivided. So you can divide it into even size subroutines. So that's pretty powerful. You can't do that kind of thing with the others. You start dealing off just portions of those structures, you destroy the structures. Okay, so the AMP structure is very special in that way. Okay, let me just make sure I know what I'm doing here. Okay, so I believe that's a AMP. That's great. Okay. Oh, yeah, we were going well, no, I guess we were going through these really quickly, and then we'll do the proof. I do want to point out there's some other really powerful things here. Two-cycle. The supercut is where you deal out and then you flip, right? And then you go into a Charlier. We did that extensively last time. This one's similar, where what you're doing is you're coding, counting out any number of cards, and then you're flipping either half. So you've counted out, say a third of them. And in fact, what's nice is it's any size. It doesn't have to be 50% or something special. So you just count out any number, and then you're free to flip either packet and then stack them however you want. And that's actually an automorphism on two cycles. That's probably a lot to take in. So why don't we just really quickly kind of show that. So once again, we're at a AMP. So recall, probably the fastest way to get to a two cycle is an LR, right? Just left, right. What's wonderful, it doesn't matter what order you stack those, it will be a two cycle. It'll be a kind of a different arrangement for the two cycle, but it's a two cycle nonetheless. And so what I'm claiming here is that you can count out, so you can go 1, 2, 3, 4, any number, 5 if you want. And then we can flip either one, and then we can random stack. Okay, so that's different than this one. You might think, well, we did that one. Well, that was pushing off. If you remember, we had to push off 50%, right? Because we were trying to go from a two cycle to a mirrored, and you have to be a little careful there, right? You can't just cut this packet in random places, right? The two cycle is invariant under packet cuts of any size. The mirrored structures aren't. Okay, so you have to be a little careful there. But in the case of a two cycle, you can actually do what I did. You just count out as many cards as you want, flip either one, and random stack. So that's pretty powerful as well. And it's just because more choices can be given to the spectator. You can say, well, how many cards you want me to deal out? 4? Okay. You want to change your mind? You want 5? You want 3? You want me to take one back? And then you'd flip either packet and randomly stack. You've done nothing to harm the structure of the two cycle. It is still a two cycle relative to your categorical relation. I mean, absolutely unbelievable. Okay, and then let's see, this one down here, 50% coat plus a random packet flip and random stack. Okay, now this one's not in the diagram. So I mentioned, so there's a couple things not in the diagram, meaning the hidden structures diagram. That's the mother diagram, right? The big one that has like everything on it. We're trying to pull off layers of this so that it's not overwhelming. So I don't have this one over here, and I don't have this really nice automorphism mentioned here on here. It's not. I must have discovered it after I created the diagram, actually. But what happens here is you do have to do a 50% coat because it is mirrored. And then if you do a random flip, random stack, it is actually an automorphism on mirrored structures. So the only difference here, so if you look at them, the only difference is the two cycle gives you the freedom to count out any number of cards, which is super nice. The mirrored structure, you have to count out half of them, okay? Otherwise, you will destroy things. And that's for the simple reason that mirrored structures are not preserved under random cuts. Under 50% cuts they are, but not random cuts. Okay, and I don't even remember what structure we have here right now. I think it's two cycle. Okay, so let's see, 1, 2, 3, 4, 5, 6. Okay, that's a 50% coat. So now it's mirrored. And so we could now do this. So you could do 1, 2, 3, 4, 5. And then it says right here, I can randomly flip, random stack. Okay, and then that will preserve whatever. Oh, I must have made a mistake there. I apologize for that. Somewhere there, maybe you guys can go back in time and see where I made that mistake. But okay, great. So I'll give that to you as a job to figure out where I made a mistake. But if you well, yeah, I mean that's not too great to. You know, we're here to build faith, right? Here to build faith here. So it's just going to show you. I mean, not that not that an example constitutes a proof. In fact, we need to get to the proofs of some of these. We're going to do one today. This is an AMP. So let's go back to a mirrored one by way of a mange. Okay, and you know that that takes it to a mange, which is sorry, takes it to a mirrored. Getting all my M's mixed up. So it is. And now what I was saying was if you count out 6, 1, 2, 3, 4, 5, 6, in fact, you can do it in hand like that. So I coded 6. You can do a random flip, random stack, and that will preserve the mirrored structure, okay? So we have 6, so we need to have a 6 over here. We have a 2 there, so we need to have a 2 right there, which we do. That needs to be a 4 and so forth. Okay, great. Maybe I'll just turn these all facing the same way. Okay, very good. So I think we've talked about all of those. I did want to quickly step through the proof because some of these more accessible proofs are very much worth doing. The ones that take just a lot of explanation, I may not include those in these videos. They may not be of sufficient interest to enough people, quite honestly. But for my students, we can prove any and all of these. Cap keeps falling off. Okay, so here's a theorem. 2 identical overcoats or overcoatings preserve mirrored structures. Okay, and what I may do here, just to help us kind of stay on track here. Okay, very good. So, get back to work there. Okay, so let P be a mirrored packet of n cards. Now, of course, n will be an even number of cards, right? I'm not sure why I have this thing underneath. Excuse me, it's causing issues. Okay, oh, it's probably to write on it, come to think of it. Okay, that'll come back to haunt me. Okay, and then if we let k be greater than or equal to n over 2. Now, because n is even, n over 2 is a whole number, right? So we're kind of safe there. That makes sense as a whole number. Okay, recall that under this assumption, the packet can be decomposed into a top portion, a middle portion, and a bottom portion. Okay, so this isn't something that I've talked about in the videos. I probably will have talked about it in class. I'll leave that over there. Now, this partitioning, this decomposition, it's really a decomposition. I don't know who originated the idea. It is used by Mulcahy when he does his work with coding. So he uses this very special decomposition, which is incredibly clever. And it actually is the basis of a lot of his proofs, actually. And I think in his book, you have to go back in the literature to this particular decomposition. Some mathematician kind of discovered it and thought it was a curious thing, but it ends up having a tremendous value in what we're doing and what he did in his book on mathematical part effect. Okay, so what's happening here is we have a mirrored structure, and then it's being divided into, so you can think of these as like kind of sections of the sequence. They're not really subsequences because that means something else, but they're a portion of the sequence. And then we're just setting them off by commas. So really just imagine a whole long sequence of numbers or elements. We'll follow this proof through with these values, and you'll see how all of the pieces fit together. Okay, so let's say our packet size is 12, like we just had a minute ago, and that we coat, we're going to use for our K, 7. Okay, so here is the suggested decomposition of the original sequence P for that packet. So what you do is you go 1, 2, 3, all the way up to, and so why don't we just make a note here? What is n minus k? Well, n is 12, and k is 7, right? So that's 5. Okay, so right here we can fill in some things. That just represents 5. And what makes all of this work is the quote top and bottom portions are of the same size. That is absolutely key to making this decomposition be of value to us. Okay, so what that would mean here is that we're looking at 1, 2, and then we're going to go up to 5. 3, 4, 5. Now, I suppose it wouldn't hurt just to at least uh, clear, explicitly write out that the sequence we have in mind, I won't write all of the values because you'll fall asleep. We're going up to 12, right? So the first 5 of them will constitute the top, the T, top portion. And then we have this middle portion. Well, all it does is it just picks up from where we left off. It's going to be n minus k plus 1. So that's just 6. And then we add another one, just this plus 2, 7. And now we need to know when to stop. We stop at k, right? Well, our k is 7. So we're done. So our middle portion only has 2 things in it. Now, if you think about it, we could have anticipated that because we only have 12 numbers. And if we've used 5 for the top and 5 for the bottom, well, there's only 2 left for the middle. And now what will happen here is this will be 8. So k plus 1 is 8. 9, 10, 11, and 12. Perfect. So and we could have calculated this as well. See, 2 times the 7, which is k, minus the 12. That's 14 minus 12, which is 2. So we kind of saw that. There's 2. Oh, by the way, these vertical lines, that means cardinality. How many elements are kind of in that sequence, that little subsection there? Okay, the question is, what's going to happen if we coat, count out, and transfer? Here would be 7 cards. Okay, well, look at what's going to happen here. So we're starting with, this is TMB. Okay, well, how many numbers are in T? 5 of them. And then M has 2 more of them. So if we count out 7 cards, or 7 numbers, let's say, we will have gone through everything in T and everything in M. And then we would be stopping there. We're done. Okay. So if you imagine, so really coding just means reverse the order. You're reversing the order of the first 7 cards, and then you're dropping the rest of the packet on top in its original order. So you haven't changed the order there. And so you can see what would happen, right? Because the top, as we deal it out, becomes the bottom. The middle will be next, and then the bottom becomes the top, because those are the ones that we just drop on top to finish things. But what's important is the cards that were in the top they're now reversed. That's what the bar means. It's like a bar for sample main, but we're using it for the elements have been reversed in order. Okay, that's all that means. And of course, if you have a double bar, then they cancel out each other. You're back to the original order. So after coding 7 cards once, this is what we would be looking at. Okay. Now, if you look at it, it doesn't really give us anything yet. But if you code one more time, the same number of cards, watch what happens. Super cool. So we're over here. This is where we are starting now. Oh, I have it right here, I guess. So if we count out 7 again, that means we will go through all of the numbers in B and all of the numbers in M. And that will be it, right? Because that's a total of 7 values. So what will happen is B will now be on the bottom, but reversed in order. M will be reversed from being reversed, like M bar bar, like we talked about. So you just get M back. And then a T gets just dropped on top, well, T bar gets dropped on top without changing its order. So look at what's happening. So after two coatings of 50% or more of the cards, we get the top back, but in reverse order. We get the middle back in its original order, and the bottom back in its reverse order. Okay. Well, what does that mean for a mirrored structure? I mean, what would that mean? So if the TMB were mirrored, what would that tell you about? So wait, I guess we can go like this. What would that tell you about this new structure? Can we deduce something from it? 6, 2, 1. Okay, so maybe just to explicitly write out a mirrored structure, here we go, 1 through 6, and then 6 through 1, reverse order. Well, we've already pointed out that the top portion is this portion right here, right? That's what we call the top. The middle was the sixth and seventh values, right? That's the middle. And then the 8th through 12th values were, quote, the bottom. So you imagine like these, so this is like the top card. You're just going down. It's always weird to think of top when we're going left to right. So if you want to draw them vertically, that could be helpful. Okay, but what's happening here? If we reverse all of these, what happens? We get 5, 4, 3, 2, 1. M stays where it is. We don't switch anything, okay? Even though here it wouldn't have made any, well, that's the whole point. Oh, that's fun to think about. we could have actually had in the proof, if the proof came out that M was reversed, it would not have undermined the result of the proof. I hadn't noticed that. That's super cool, but not important here. Okay, so that stays where it is, and then these get reversed. And then look at the overall structure. It started out mirrored, and it ended mirrored, right? Look, we get 5, 4, 3, 2, 1, and a couple of 6s. Now, it's not the exact same, it's being scrambled, right? Things are being permuted. But this is an honest-to-goodness mirrored structure relative to the categorical relation that the cards have the same value, or that the numbers have the same value. If you want to think of them as numbers, that's fine too. Okay, so we've just verified that two identical overcoats indeed will preserve a mirrored structure. Okay, so I think that's pretty slick that it works out that way, and performing just two coats isn't too exhausting for anyone, actually. Okay, well, I think we're going to call it a day, and so I encourage you, really the only, I want to say that it's not going to be all that difficult to master these, because once you see what's going on, you can see what the next step has to be for you to arrive at your destination, and that if you don't do a certain next step, you won't get there. So if you have these down, the original ones, and then you kind of slowly introduce these, you can really master all of those. You really can, and they're kind of self-reinforcing as you use them. So I encourage you to, really put some time in. They've shown that with learning, cramming is not the best way to go for long-term retention. The very best way to learn something long-term is to study in kind of reasonable time intervals over a long period of time. So to have breaks, so to kind of walk away from things for a while. Because I think the biology of it is your neural pathways will be strengthened if there's been some time in between kind of repetitive practice. And it's almost like you're having, it's in the act of remembering that powerful neural networks are created. It's when they call it effort powerful recall. So if you have to make a little bit of effort to remember something and you successfully remember it, you are strengthening your neural pathways tremendously. Okay, so that's actually when the real permanent kind of encoding happens in your brain. I don't know how many different kind of metaphors we can use for describing this miraculous process that we probably really don't understand fully. But there are things about learning that seem to be reliable. And so one is to set aside kind of fairly short periods of time to practice ideas and recalling them and so forth, and then have periods of time to rest from doing that and then come back to it and see how well you do. And if you do that over a week or two or three or four, you can actually render permanent many of these ideas. And one of the reasons for that being possible is that what we're showing you is very tactile, right? There's motor skills involved. And it's just like riding a bike. I mean, you can go 30 years and not ride a bike, and just within minutes, you awaken, parts of your brain, and you suddenly kind of get some degree of balance back and dexterity, and you're riding a bike again. And it's been a long time. So it's almost like we remember things not only in our mind, but in our muscles as well. That seems to strengthen our hold on new ideas. So the fact that all of this is so tactile, I think is a powerful, powerful advantage to helping people remember these things long term. Okay, well, I better go. It looks like the sun's going down and the light's dimming on our recording here. So, okay, so we'll see you next time.